Hello, hello, hello. We're back again. It's 1.3, separable first order ODEs. So let's try to make a nice little short video to introduce us to this topic, okay? Here we go. We are still talking about our nice first order ODEs that can be written as y prime equals f of x and y, right? What is this, right? Our dependent variable is y, good. Our independent variable is x, nice, right? Easy to tell. Taking a derivative of y, he's the dependent, right? X is involved, he's the independent. Our unknown function is y as a function of x, yes? Okay, so unlike what we have been doing, now we're actually going to start solving differential equations. And separable first order ODEs are super cool because they allow us to solve lots of differential equations that are first order, provided we can write this function as a product of a function of x times a function of y only, right? So you are separable if we can separate the function of x times separate as a function of x. We can separate this all mixed up function instead as separated as a function of x times a function of y. So function of x times a function of y. Yep? All right. So the question is, right, can we write this as, and I will not use the letter f again, so I'm just deviating from the book again, as some function, let's call it h of x, times some function, let's call it g of y. Okay? So if I can look at this right-hand side and factor stuff out, right? We've been talking about factoring, so important. Be able to write it like this, then I'm golden because this is separable. Okay, now y, let's think about this. Right, what does y prime mean? Okay, well it means the derivative of y with respect to x, like we reviewed the last several times. So we got this, right? Why can't we just straight up integrate this equation right now? Well, right, it's this guy, g of y. If there's a y over here, we can't integrate because we're integrating with respect to x, right? And this is some unknown function of y, right, in here. So that's not legit, okay? So this is the derivative form of our differential equation. Okay, but kind of just like our u substitutions that we talked about the other day, we could write this in a differential form. So a differential form of our differential equation, okay? So this guy says the rate of change of y with respect to x is equal to the product of these two functions, h of x times g of y. But we also could look at like how a small change in y is related to a small change in x, right? That's our differential form, right? So tell me, what is the differential form of this equation? Good. Y is h of x times g of y x, right? That's the differential form. Well, now the goal is, well, can I utilize the idea of this differential form to get everything with an x on one side and everything with a y on one side, right? So I want to separate the variables, thus the name. Okay, separate the variables. Everything that's dependent variable on one side, everything that's independent variable on the other, right? So what would I need to do that? Good, just divide by g of y. divided by g of y is h of x dx, right? Yeah, so let's write that up here. So that guy becomes, so the differential separated form is, that's a y, sorry, dy over g of y is equal to h of x dx, okay? Now, this is some function of h, and we're talking about h with respect to changes in x, and this is the same as 1 over g of y, so let's write it that way. 1 over g of y dy. So these guys themselves are each separately integrable, integrating this guy with respect to y and integrating this guy with respect to x, right? And then I'll get a plus c that I can throw on to the end after my integrations, and then I'll have a relationship between y's and x's. So let's just look at an example, okay? And we can see how we do this for some specific problems, yeah? Okay. Make sure I did not say something I didn't say. Okay, let's look at okay. Plus C up there, so it's okay. So this is one of the exercises. Let's look at exercise 1.3.5. So here we have an equation. The derivative of y with respect to x is x times y plus x plus y plus 1. So if we think back to what we've been doing, this equation with slope fields might just be a little ugly. Yeah? I mean, it's not super nice, like written the way it is, okay? So it might not be fun to draw out. Now, what do I have? This is my f of x and y, right? This is a function of x and y. What does it say? That f of x and y says take x and y, multiply them together, add x, add y, then add 1. That's what that function says, right? What does this differential equation say? It says find me all functions out there in the world whose derivative with respect to x is x times itself plus x plus itself plus 1. Well, you could try guessing like we did on the first day of class, yeah? Guessing isn't probably going to get you far, right? Okay? So, what are all functions out there in the world whose derivative would satisfy this crazy thing, this crazy relationship between x and y, right? That's what that f of x and y means. All right, well, what do, right? We don't want to do slope fields because that just seems like it's going to be a lot of work, and the only thing we have is separable. And so we want to see if we can write this as a product of two things. One only depends on x and one only depends on y. Not looking so good right now, but if we, put on our super factoring glasses, right, you might notice, right, if I just factor in x out of these two guys, then what do I have? A y plus 1, oh, and then there's another y plus 1 sitting out there, so we can kind of play that same trick we played the other day, the other video, and pull a y plus 1 out of both of these guys, and if we do that, y plus 1, what's left in this guy? X, what's left in that guy? 1. Yeah? Are we all good there? So, our equation, derivative of y with respect to x, given to us this way is equivalent to this, and this we like, right? Why? Because we've got a function of y only, doesn't matter what order they're in, right? Times a function of x only, yeah? And whenever we can separate this guy so that it's just a product of two separate functions that depend on different variables, x and y, in this case, then we can go from our derivative form of our ODE to a differential form, right? And often we'll kind of skip, well, not all the way to there, but a lot of times, it's up to you how many steps you feel like you need to put in, right? So if I'm gonna write the differential form of this guy, then what do I want, right? I've got dy over y plus 1 is equal to x plus 1 dx, right? Okay, dx comes over here, and the y plus 1 goes over there, yeah? So there's our differential form, okay? Clearly, let's be clear here, we're not multiplying by dx, right? Dx is not, this is not a fraction, right? The derivative of y with respect to x is the derivative operator, derivative with respect to x, applied to y. This is all one operation, derivative with respect to x, right? Okay? But if that's the way you have to think about it, multiplying by dx in order to get to your differential form, then just do that and don't tell me. All right, so here we go, right? Now we have something that looks like that, and so what do we want to do? We want to integrate both sides, yeah? Right? We're just going to integrate each side. So I'm just going to put in another step just so that we see what happened, right? Whoops, yes. Yeah? All right, this side is probably pretty simple, right? For you to integrate. So what's the integral of x? Right? Add 1 to the exponent, divide by the new exponent. So 1/2 x squared, yeah? X squared over 2. Right? What's the integral of 1 with respect to x? 1 with respect to x is x. Yeah? Really, you don't add 2 arbitrary constants, right? An arbitrary constant is an arbitrary constant, so we'll say plus c. You add 1 arbitrary constant. I like to stick them over on the right. With x, okay, and now it's a matter of, do we remember how to do this integral, right? Okay, so what's the integral of, we did this before, what's the integral of dx over x? Good, the natural log of the absolute value of x plus c, right? What's the integral of dy over y? Good, the natural log of the absolute value of y plus c, right? This one is one we probably did a lot in calculus, right? We got pretty good at it so that we didn't have to go to a u substitution. If you did a u substitution, you would let u be y plus 1, du would be dy, right? So then you would turn this into the integral of du over u. What is the integral of du over u? Yay, the natural log of the absolute value of u plus c, right? You gotta have the absolute value in there. Things could be positive or negative, right? And so then we go back to the fact that u was y plus 1, and so then we get that this guy is the natural log of the absolute value of y plus 1, right? Plus c, but he's over here, we already put our plus c in there, so that's where this guy is coming from, the natural log of the absolute value of y plus 1. These types, you're gonna wanna, make sure you can do those relatively quickly, not have to go through that u substitution, right? If there had been a constant multiplying u, or multiplying y, then you have to be a little bit more careful because you're gonna get a constant in there. You may wanna go to a u sub. But when it's y plus a constant, you're golden, yeah? Okay. So here we've integrated both sides. So what do we have? We've got a relationship between y and x that satisfies this derivative request, right? That's what an ODE is. It's a derivative request. Hey, I want the derivative to satisfy this equation. Okay? So any function that satisfies this relationship between x and y will satisfy that. Well, we call this an implicit solution. This is an implicit solution. Of the ODE. Why? It's only an implied equation. It's not explicit, right? for y of x equals, right? We want to say y of x is this function of x, and it only depends on x over here. We don't have that, right? We just have a relationship between y and x, right? A relationship between y and x, okay? So sometimes an implicit solution is all you can get because the integration just turns out to make, you know, an equation which you can't solve explicitly for y as a function of x. But here we can, so we will, right? Okay? So, but we can come up with an explicit general solution of the ODE. So let's do it. Let's do it, right? It's the general solution, right? There's infinitely many solutions here, okay? So this is also something that can often be somewhat confusing to students. So here's another reason why we're doing this as well. Okay, so we have that solution right there. What would we want to do? We want to solve it for something explicit, right? What does explicit mean? It means y as a function of x is equal to stuff that only depends on x, right? Stuff that only depends on x, yeah? So what do we need to do? Good, I heard it there. We got to eat both sides, right? We got to get y out of inside the natural log, yeah? Okay, so we got to take the exponential of both sides. So I'm just going to write that. So we're going to say e to the natural log of the absolute value of y plus 1, right, is equal to e to the what? 1/2 x squared plus x plus c. Whoops. Yeah? Right? You do one side, you do the other. Okay? So the whole point of doing this, e and natural log are inverse functions, right? So the whole point was, right, to also review that. And e and natural log are inverse functions. So what do I get out of this? Absolute value of y plus 1, right? Yes, must keep your absolute value. All right, that's what I get because e and l undo each other, right? So what do I have over here? E to the 1/2 x squared, or I'm just going to write it as x squared over 2 because it's less writing for me, okay? Plus x plus c, right? Yeah? Okay, e's raised to that whole thing. Okay, you can put it in parentheses if you want or not, as long as you make it clear it's up in the superscript. All right, so this is still not an explicit solution, right? Because we got the absolute values there and we can't get rid of them, yeah? Now we talked a little bit about what the absolute value function means, so we could introduce a piecewise function, just like we did in the last video where we talked about, okay, well, we could say that that means this, but if we can get away without having to do that without having absolute values, we want that. All right, so let's think about this. This guy is always positive, right? Okay? And this guy is always positive. Yeah? Okay? Well, okay, e to anything is always positive, right? We're good with that. Now this guy, you're like, hey, wait a minute. What if y were, oh good, I heard it out there. What if y were, yeah, -1, right? If y is -1, then this is 0, right? And this wouldn't make any sense, because can 0 equal e to anything? If y is -1, so that sounds like y -1 is something to pay attention to, right? Now let's think about y equals -1, okay? Well, over here, clearly y equals -1 is an issue, right? Because we'd be dividing by 0, yeah? Okay? So this solution makes no sense if y is -1, yeah? We're good? Awesome. Now, let's keep doing this little aside here. What about y equals -1? Is y equal -1 a solution of the ODE? It makes no sense in here, so it does not follow from that process, right? But from this process, we kind of identify this kind of singularity, right? Division by 0 would be bad, right? Well, let's think about y equals -1. Okay, well, if y is -1, what is dy dx, right? Well, 0, right? And what is x times y plus x plus y plus 1? Well, it's kind of crazy to go to that, right? Let's go to our nice factored form, right? If y is -1, right? What do we have? What is y equals -1, right? Very good, good, right? I'm just trying to figure out how to write this, right? I guess I'll just write it equals -1 plus 1 times x plus 1, right? Right, which is 0, right? And so y equals -1 is a solution. Obviously, we could have just looked at this and said, hey, wait, y equals -1 is what kind of a solution? So the answer is yes. And then you want to say y equals -1 is an equilibrium solution. Yay, right? Okay, an equilibrium solution, yeah? Okay, so this is an extra solution, okay, to our differential equation, which is not included in this implicit solution to the ODE, right? Okay, and so we would also need, right, and y equals -1 if we wanted to claim that was a general solution, yeah? These guys are called singular solutions too because it doesn't appear in here. Okay, so back to this. How do we rectify this problem? Okay, first of all, the problem we really want to rectify, this is positive for y not equal to -1, right? Because otherwise it's 0 and absolute value is always positive. Back here, yes, you guys with me? Here we go. What do we do? Okay, so let's just do some more refreshing what we can do with exponentials. So we have the absolute value of y plus 1 is where I got right here. And then I've got, okay, rules of exponentials. E to the x squared over 2. Yeah. Let's see why we're going to do this here in a sec. E to the x squared over 2. I got all the summing. When I have e to stuff and I'm summing, that's the same as multiplying, right? Times e to the x times e to the c. Yes? Do you guys agree? That and that are the same. Yeah? Okay. So this is still positive for y not equal to -1. This is still positive because e to anything is always positive, right? Okay. All right. So now, like, what's the deal with this guy? If I drop the absolute values, he's either positive or negative, right? So if I want to be able to write this without the absolute values, then I can't have, now notice, c is an arbitrary constant, so e to the c is also an arbitrary constant, right? So if c is an arbitrary constant, right, so we could say back here where c is an arbitrary constant. E is a specific constant. E raised to an arbitrary constant is an arbitrary constant, yeah? Okay, and so if we're going to drop our absolute values here, then this guy, right, we really would want a plus or minus in order to deal with that, but we don't want plus or minus in front of that because this guy always has to be positive, so we could just call it another letter, let's say d. So we have d, e to the x squared over 2 times e to the x, yeah? Or we could just leave this as e to the x squared over 2 plus x, yeah? Same thing, yeah? And then we can just leave that guy alone, yeah? But this gets to be like annoying and takes like a lot of letters. And so what we generally do in differential equations is like, oh, I'm going to redefine c. I'm going to make this an arbitrary constant now. And so I'm just going to call it c because I like c better than d. And this c is different than that c because they can't be the same thing because it's obviously clear, right? Yeah, does that make sense? Okay, so now this is a new c, arbitrary constant, right? So we don't keep adding in different arbitrary constants, but you got to be a little bit careful when you're doing this because when you start evaluating initial value problems, you got to be a little bit careful if you start plugging in other places and then you redefine what your c means, okay? So now we're super close. What is y? Y is c e to the x squared over 2 plus x minus 1, right? Subtract. And now we have y given as an explicit function of x, yeah? Does that make sense? Y is an explicit function of x, right? And tell me, remember our friend, y equals -1? That was an extra solution that didn't appear in the implicit solution of that guy, right? Okay, that we had to remember to worry to think about our equilibrium solution, yeah? Is that included in here? Yeah, right, okay, so this guy's our like explicit general solution because what? If C is 0, then our y equals -1 is in here, right? C equals 0 gives us our y equals -1. So the solution y equals -1 is in our explicit solution, yeah? Make sense? Alrighty, so what else do I want to do before I wrap this up for you guys? Maybe nothing at this stage. Yes, maybe we would just quickly add in solving an initial value problem. So, what is the solution to y dx equals this guy, right? Y plus 1 times x plus 1, right? Or this guy. Again, these guys are going to satisfy Picard's theorem, okay? So everything is nice. So is the partial derivative with respect to y. Everything's nice and continuous. And let's add in y at 0 is equal to 5, right? So here's our initial value problem. There's our explicit solution, right? Okay, and so what do I find? I'm going to plug in 0 to evaluate the initial condition, right? What is y evaluated at 0 over there? It's c times e to the 0, right? Minus 1, which is c minus 1. And what do I want c minus 1 to be equal to? 5. And so what is c? C is 6, right? So therefore, what is the solution of the initial value problem, right? Y is equal to 6e to the x squared over 2 plus x minus 1. That specific function goes through the point 0, 5. Yeah, does that make sense? Okay. I hope you have had fun. Yeah, I hope you've had fun. In our first intro to separable differential equations, we'll be looking at just a couple of other things related to this, so there'll be another video coming. Let's just make a point over here. I knew there was something else I wanted to say. Talking about the different C's, right? If we thought about that y of 0 equals 5, and we were plugging it in over here, right? What does that mean? When x is 0, y is 5, right? So that would say c would be the natural log of 6, right? Okay, in this problem. Yeah, does that make sense? Okay. So even with an implicit solution, you can evaluate an initial condition by plugging in the particular values for x and y from the initial condition to solve for the constant c, if all you have is an implicit solution. Does that make sense? What's the solution to? What if we said, what's the solution to y of 0 equals -1? How about y of 300 equals -1? What's the solution to that one? Good. Just y equals -1, right? That's the equilibrium solution, yeah? No matter where you are, if you start on that solution, you stay on it. Y is -1. All right.
enough for today. Thank you, and I will see you soon.